A little bit about interval notation. We'll need interval notation on the front end here for solution sets to linear inequalities. We do nonlinear inequalities in future math classes, do linear inequalities in this one, but inequalities in general, typically you don't have a handful of solutions, you have an interval full of solutions. Maybe all the real numbers in between two numbers, or all the real numbers that are to the right of some number on the number line, or to the left of some number on the number line, or maybe all real numbers. We can't describe, usually, we can't describe solution sets to inequalities by just saying, well, it's 5, and it's 6, and it's 14, and put set braces around. They just don't come like that. So, for intervals, I try to break these down into two basic categories, the bounded intervals and the unbounded intervals. There are other ways to further subclassify them. These are the bounded ones. Bounded means they don't go all the way to the right, they don't go all the way to the left. They have both a left-hand endpoint and a right-hand endpoint. So let's look first at how to describe the set of real numbers in between two numbers. A is less than x, and x is less than b. A couple different ways to do the graph. And I'm not going to ask you for the graph. Alex may ask you for the graph. I'm not going to ask you for it, but I would like you to recognize two different graphs here. One way to do it, and I think the Alex way, probably going to say put an open circle at A and an open circle at B, indicating that A is not in that interval and B is not in that interval. But everything in between is in the interval, so shade everything in between. That's the way I learned it in high school, back whenever it was that I went to high school. You put open circles to indicate that the endpoints are not included. Now, this doesn't translate all that well to the interval notation. Interval notation is going to be the preferred way of expressing the solution set. I'm going to ask you for the interval notation on the test, so that's what you want to give me. It's the preferred way of expressing the interval, and this particular style of graph does not translate well into interval notation. So instead of the open circles, I'm going to ask that you use parentheses. Parentheses. A parenthesis indicates that that's the left endpoint or the right endpoint, and the endpoint is not included. It's not part of the interval itself. So you put the left endpoint, the right endpoint, shade everything in between. And when you want to translate that to the interval notation, all you have to do is put the parenthesis on the left, the parenthesis on the right, the A on the left, because the A is on the left. It's the left-hand endpoint of that interval. And the B is on the right, A comma B. And a quick word about notation. Sometimes we use two different notations. It can be frustrating when we use two different notations that mean exactly the same thing. For example, this graph means exactly the same thing as this graph. It's also frustrating when we use a notation that actually means two different things, depending on the context. You know that if we have a point in the plane with an x-coordinate of A and a y-coordinate of B, we denote that point how? How do we write that? Yeah, A comma B. That's exactly the same notation that's used here, and it means something completely different. In this context, it's a point with an x-coordinate of A and a y-coordinate of B. In this context, it's an infinite number of numbers on an interval in between A and B on the real number line. And it's just a matter of understanding that if the context is an interval, if a particular statement, if it's an inequality and it calls for an interval, it's this, that's what it means. And if it calls for a point in the xy plane, it's that. So it's the same notation that's used for two very different concepts, and the important thing is to understand the context and the difference between the two things that it might represent. Now, if both endpoints are included, it's a little bit different notation. The endpoints, if it's Alex, Alex probably wants a solid dot right there and a solid dot right there to indicate that the endpoints are included. What I'm looking for is a square bracket at both ends to indicate that the endpoints are included. The reason? That translates well to interval notation. If you want to write this interval using interval notation, you put the A on the left, you put the B on the right, and indicate brackets. A belongs to that interval, B belongs to that interval. If neither endpoint is included, we call this one an open interval. If both endpoints are included, we call it a closed interval. They don't all have special names, but those two are kind of special. Neither endpoints on a bounded interval is open. Both endpoints included on a bounded interval, closed. What if one endpoint is included and the other is not? Well, if A is included, then we put a bracket, closed bracket next to A and a parenthesis next to B to indicate B is not included. Notice how we can tell the inequalities. This one has the or equal to bar. A is less than or equal to X. So A is good. This one does not. It's a strict inequality. X has to be less than B. It cannot equal B. So that's why B is not included. We include the A. We do not include the B in the interval notation. And if B is included and A is not, of course it goes the other way. And it looks like that. So if neither endpoint is included, it's open. If they're both included, it's closed. If one is included and the other is not, what do you think? Is the interval half open or is it half closed? It may depend on your outlook on life. You know which way you want to go with this. Is it half open or is it half closed? I don't know what this says of most mathematicians, but typically they describe the interval as being half open. Would that be a positive way of looking at it or negative? I don't know. But that's the way it shows up in most textbooks. These are half open intervals. These are the bounded ones. Have a left-hand endpoint. Have a right-hand endpoint. Don't go off to infinity in either direction. You can kind of wrap your arms around them. Give them a big hug if you want to. The others are unbounded. Let's see if I can put them on the screen. Unbounded intervals. Did I say bounded there? Bounded, yes. These are unbounded. There we go. Everything greater than or equal to A. If we want to describe a set of real numbers that are either at or to the right of a particular number, X is greater than or equal to A, we use a square bracket to indicate that the left-hand endpoint is included and there's not a right-hand endpoint. To translate that using interval notation, we use the square bracket and we put the A on the left because it's on the left of that interval. Nothing on the right. It goes infinitely far to the right. So what do? Use the symbol for infinity. And we put it on the right because that's the direction of unboundedness, to the right. Always a parenthesis next to an infinity because it's not actually a real number. It's just a symbol that we use to describe unboundedness. It goes on and on and on without bound, no right-hand endpoint. If the left-hand endpoint is not included, we put a parenthesis, but otherwise it looks pretty much the same as the one in which it is included. If it's everything less than or equal to a particular number, put that number on the number line and shade everything to the left if it includes the A. Square bracket there. Sorry, square bracket there. No, I was right the first time. On the left. It's hard to kind of reverse that sometimes. So we put it, I'm using the word left. It's actually on the right there, isn't it? A is the right-hand endpoint of this interval. What's the left-hand endpoint of this interval? Right. Well, the answer is there's not one. But because there's not one, we put the symbol negative infinity. Whenever we put in negative infinity, it's always on the left to indicate unboundedness to the left. Never want to put negative infinity on the right because that's just kind of contrary to what we're trying to say. You put the infinity symbol on the right, and that indicates unboundedness to the right, and you wouldn't want a negative sign there because that's where the positive numbers are on the right. So negative infinity to A without the bracket, and it looks like that. Now there will be several occasions where the set of real numbers that we're talking about is all of them except one particular bad value of x. When we look at domains of rational functions, section 3.5, this will occur time and time again. There's just going to be one bad value of x, and we want to exclude that one and allow inclusion for everything else. This is not a single interval, so we can't describe it using a single interval. It's everything to the left of A together with everything to the right of A. It's two intervals. They don't overlap. And their union includes everything but that one bad value of x, A. So we use the symbol for union. It's convenient that it kind of looks like the letter U. It's not the letter U. It's a symbol for union. And basically it's everything that's in here or everything that's in here. It's everything that's in either one of those two intervals. That's what's in the union of those two intervals. So that's two separate intervals, not just one. And the set of everything, all real numbers. I say everything, then I'm about probably to talk about a set of complex numbers in a little bit. Set of all real numbers looks like this. So these are the unbounded intervals. Want to be able to translate from inequality notation to interval notation, be comfortable going there, or if someone hands us some interval notation, we want to know what that means. And probably in both cases, whether we're going from inequality notation to interval notation or back again, sketching the graph just as a frame of reference is not a bad idea. I'm not going to ask you to sketch the graph, but I think if you will draw the graph so it's clear in your mind what interval you're trying to describe, it'll be easier to translate that to interval notation. So from -3 to 3, on the number line, we're talking about everything from, I hope I said -4. It sounded like I said -3. Everything from -4 to 3. On the number line, we're trying to describe the numbers in between these two numbers, including the 3, but not including the -4. Now the interval notation, we take this and we put a parenthesis on the left, and then we put a -4 on the left, because -4 is on the left. And then we write a 3 and put a bracket on the right, because 3 is on the right. This particular interval, that's the interval notation. Yes?
So if this question was on the test, would we be required to put the line there, or would we be required just to put the interval notation?
Just the interval notation, that's it. That's just it. X greater than or equal to 5. And just a lot of times students will be confused about which number goes on the left and which number goes on the right. And just looking at the inequality notation, I don't know that it's immediately clear to me whether 5 is the left-hand endpoint of this interval or the right-hand endpoint of this interval. I mean, just today I've gotten my left and right confused a little bit. So I think if you do take the time to draw the graph, then to the point where you can see 5 is on the left, then when you write the interval notation and you're sure to put 5 on the left, the rest of it should go well. It doesn't hurt, but it's not necessary to draw the graph if you know what you're doing. That's just more work. X is less than -1. -1. And we're trying to describe everything to the left of -1 on the number line. So this one's the trickiest one. This is the most frequently missed one. You look at it and ask, is -1 on the left, at the left endpoint of this interval or the right endpoint of this interval? Well, certainly on the right. So it goes on the right when you write the interval notation, and there's nothing on the left. This interval is unbounded to the left, so you put the -infinity there. That's the final answer there. And to describe the interval, it's everything but the number 3. Well, I don't even know if I need to draw the graph there. It's everything to the left of 3 together with everything to the right of 3. The graph may actually help, I don't know. There's a 3, there's everything to the left of 3, there's everything to the right of 3. Just leave out the 3. Negative infinity to 3, union 3 to positive infinity. My union symbol may be a little bit on the pointy side there. Now it's a little flat, but that's okay. Union of these two intervals. A little bit more of the same, just from the opposite direction. In the next example, I think, someone hands us the interval notation, and we got to look at that and figure out, well, what does that mean? What set of numbers on the number line are we talking about here? And I think it's good to draw the graph in addition to writing the inequality notation. Negative infinity to 3. So there's the number line, and there's 3. Are we talking about numbers to the right of 3 or to the left of 3 here? To the left. That is correct. Negative infinity to 3. So in inequality notation, to the left of 3 means x is less than or equal to 3. Like that. Negative 2 to 4. Well, that's an easier one because the way the interval notation is written, negative 2 goes on the left and 4 goes on the right. And it's just a matter of indicating the bracket there and the parenthesis there. I don't know that we use, before college algebra, a whole lot of three-part inequalities. I remember my freshman year in college when I took calculus class, and the professor was using three-part inequalities. I thought, well, it's kind of cool, but I've never really seen that before. And I had taken a lot of math classes in high school, but three-part inequalities might be new. It might be something that you've just seen so much of that you really don't want to see anymore, and maybe I wouldn't blame you. But just think between, shading in between, negative 2 and the 4 means x has to be in between negative 2 and 4. So put negative 2 on one side, 4 on the other, and just make sure you put the or equal to bar next to the one that has the bracket. So negative 2 is less than or equal to x. Negative 2 is good. But x has to be strictly less than 4. So there's your inequality notation for that one. 5 to positive infinity hopefully is not too bad. Put a 5 there. Is this everything to the left of 5 or everything to the right of 5? Together with the 5, of course. To the right of 5, so we include the 5 and go to the right. So x has what relationship to 5 here? Greater than or equal to 5. Excellent. And then the open interval at the end, negative 2 is on the left, 3 is on the right. Neither the negative 2 nor the 3 is included. And so x is between negative 2 and 3. So negative 2 is less than x. X must be less than 3. Basics there of interval notation. Now, a lot of words here. I'm going to move quickly past this in case you're trying to scribble all that down. A lot of words with properties of linear inequalities. They're not unimportant, but boil it down. There's some really key things you need to look at that distinguish solving a linear inequality from solving a linear equation. I like to do this, and sometimes I think it's helpful, hopefully all the time. 4 is less than 6. True or false? It's true. Now, what if we add 2 to both sides? Sometimes you're solving an equation, you're solving an inequality. You need to add the same number to both sides. If I put a less than there, is it still true? Yes, it is. I think of it as kind of a balance that's unbalanced. 6 is heavier. 4 is less than 6. And you add the same amount of weight to both sides. It's still unbalanced, and it's still unbalanced in the same direction. So 6 is less than 8. Yep, sure, absolutely. Still true. 4 is still less than 6. What if instead we subtract 2 from both sides? Still less than, still true. 2 is less than 4. It's unbalanced. You take the same amount of weight off of each pan, and it's still unbalanced in the same direction. Good. When solving a linear inequality, or any kind of inequality, you can add the same quantity to both sides, subtract the same quantity from both sides. It does not affect the direction the inequality symbol is pointing. It will give you an equivalent inequality. 4 is still less than 6. How about if we multiply both sides by a positive number like 2? 2 times 4. Compare that to 2 times 6. If we put a less than, is it still true? 8 is less than 12. Looks pretty good. 8 is still less than 12. Multiply both sides by 2. Still good. 4 is still less than 6. How about if we divide both sides by 2? If I put a less than, is it still true? Yes, it is. 2 is less than 3. So what's going on here? Let's see. There's 0. There's 2, 4, 6, 8, 10, 12, negative 2, negative 4, negative 6, negative 8, negative 10, negative 12. So let's put maybe a red 4, and a green 6. There's 4. Whoops. There's 4, and there's 6. If we take that inequality and multiply both sides by negative 2, negative 2 times 4, negative 2 times 6. If we put a less than, is it still true?
No.
This is the case where it becomes necessary right at the moment where we multiply both sides by a negative number to reverse the direction the inequality symbol happens to be pointing. Negative 8 is actually greater than negative 12. It's to the right of negative 12. Where is negative 8? So 0, negative 2, negative 4, negative 6, negative 8 is right there. And where is negative 12? Negative 12 would be about right there. So you see a role reversal. 4 is to the left of 6. But when you multiply both sides by negative, and you see where those two numbers end up after multiplying by the negative, it's reversed. So we've got to reverse the direction the inequality symbol is pointing. How about 4 is less than 6? Last thing to do here, divide both sides by negative 2. 4 divided by negative 2, 6 divided by negative 2. If we put a less than, is it still true?
No.
We must reverse the direction the inequality symbol is pointing. So what do we get there? Somewhere there is a negative 3. That'd be right there. And somewhere there is a negative 2. And again, it's the reverse direction. On the 4 is less than 6, the red one was on the left and the green one was on the right, but multiply both sides by negative, role reversal, the green one's on the left, the red one's on the right, so we have to reverse the direction the inequality symbol is pointing. Whenever multiply both sides of an inequality by a negative number, or divide both sides of an inequality by a negative number, if we want an equivalent statement, and we do, otherwise the solution set changes. We want an equivalent statement to preserve that. Got to make sure we reverse the direction the inequality symbol is pointing right at that moment. All right. Example 2. I don't think this is really all that new. This is what we do actually early in the semester in intermediate algebra. But let's make sure we're still good with this. A little bit of distributive property, a little bit of combining of like terms, and perhaps we'll have an occasion to multiply or divide both sides by a negative number. The key here is find the solution set. X is maybe greater than or equal to something, or maybe less than or equal to something, and translate that to interval notation. Let's see if we can get there. 7x plus 7 minus 6x plus 2x is greater than or equal to negative 4 plus 2x. Negative 2 times negative x, positive 2x. All right, the plus 2x. Simplifying both sides does not require us to reverse the inequality symbol. So keep simplifying. Combine like terms. There's a 7x, there's a negative 6x, and there's a 2x. How many x is that on the left? 3x. 3x plus 7 is greater than or equal to, I guess it doesn't matter what comes first, so I'll just keep it negative 4 plus 2x. Oh, wow. This is unnecessarily trivial. Gee whiz, what a waste. I'll follow through with it. What do we do next? Wow. Can't believe I took class time for this problem. Subtract 2x from both sides, subtract 7 from both sides, and what happened? X is greater than or equal to negative 11. Is that really what happened? That's really what happened. No occasion to multiply or divide both sides by anything, because we came up with the x on the left-hand side. Sorry, I'm not doing a good job of masking my disappointment. I had different intentions for this problem. It's my fault. I made up the problem. How do we write this in interval notation? Let's salvage something from this. What do we write?
Close bracket. Negative 11 below x open bracket. Or appendix.
There we go. Negative 11 to positive infinity. That's what this looks like. And if we need the graph to show us what's going on, that's a set of numbers, but that's what I want for the solution set, the interval notation. Wow. We'll have an occasion to divide both sides or multiply both sides by negative here in a little bit. Didn't happen there, though. We look at a couple of compound inequalities in example 3. There's room for both of them on this page. Compound inequality, or compound mathematical statement, is basically the two mathematical statements that are joined using a connective word such as or and. Those are the typical ones that we might use, or and. If we use the word or, in order for the statement to be true, both components of the statement have to be true. Wow. Did I just not get enough sleep last night? I'm so sorry. If we use the word or is way more flexible than and. Not nearly that restrictive. Or is easygoing. If you want the statement to be true, either one can be true. And it's good. So if the statement on the left, we find an x that makes 3x minus 5 greater than or equal to 7, that makes it true. X is good. It belongs to our solution set. If we find an x that makes 5 minus 2x greater than or equal to 1, x is good. It belongs to our solution set. So our plan is to solve each of these inequalities, get a solution set and maybe an interval for each one, and our final answer is going to be the union of those two intervals. If they overlap, it might just be one great big interval. But if they don't overlap, it will be the union of those two. The B part, I should go ahead and make the distinction, that's the one that's restrictive. Because it's and, x minus 3 has to be less than 5, and 7 minus 2x has to be less than or equal to 3. They both have to be true in order for the compound statement to be true. And so we might get an interval for the one on the left, and we might get an interval for the one on the right, but it's got to be what those two intervals have in common. It's going to be where they overlap. And if they don't overlap at all, then we've got no solutions at all to that compound inequality. So the or is easygoing. Either one can be satisfied, and oftentimes it's the union of those two intervals. The and is restrictive, and it's got to be what those two intervals have in common, if anything. So let's solve these components and then put them together and find the solution sets. 3x minus 5 is greater than or equal to 7. Let's add 5. Let's add 5 to isolate the x on the left-hand side, the x term. 3x is greater than or equal to 12. And what? We divide both sides by positive 3. No need to reverse the inequality symbol yet. So x greater than or equal to 4. That's one possibility. We'll write an interval notation for that in a little bit. The other one, subtract 5 and subtract 5. Negative 2x is greater than or equal to negative 4. Divide both sides by negative 2. Now, I like to write a fresh copy of that negative 2x and a fresh copy of the negative 4. If I just put a line under the negative 2x and the negative 4 and divide both sides by negative 2, that inequality really needs to be erased and reversed at the moment that happens. So an extra fresh copy of the negative 2x and the negative 4, no need to erase the inequality symbol above, just write the new correct one up underneath. So x could be less than or equal to 2. The word or actually could come down at every step. When we add 5 to both sides there or subtract 5 from both sides there and get those equivalent inequalities, we could write the word or there, and this statement is equivalent to the one up above. When we divide both sides by 3 there or divide both sides by negative 2 there, we could write the or there. We could write the or there. This statement is equivalent to the one at the very top. So the solution set, yes.
Wait, doesn't x have to be less than 4? Less than or equal to 4? Because we didn't switch it.
On which one?
On the first one of A.
We didn't change from negative.
We're dividing both sides by positive 3.
Okay.
So that doesn't require us to switch in that case. So we've got 4 to positive infinity. Any number that's greater than or equal to 4 is going to make the first inequality true. We've got negative infinity to 2. Any number that makes 5 minus 2x greater than or equal to 1 has to be less than or equal to 2. If it's less than or equal to 2, it's going to satisfy the top one. Once I write the intervals, I'm going to change from the or to the union of these two intervals. And it would be okay to leave the final answer like this. I think a slightly better way to do it would be to write the interval that actually appears on the left on the number line, put that on the left, and the one that actually appears on the left on the number line, and put that on the right. But either one of those, that or the statement immediately above it, should be fine. And we know what interval we're describing here. Everything less than or equal to 2 together with everything greater than or equal to 4. The only numbers that fail to satisfy this compound inequality are the ones between 2 and 4. Everything else is good. B part. Add 3 to both sides. X is greater than 8. Less than 8. No switching of the inequality just by adding 3 to both sides. X is less than 8. The other one, subtract 7. Again, no switching of the inequality, just subtracting the same number from both sides. So it's still less than or equal to. And I'm going to bring down the word and. In order for x to satisfy this compound statement at the top, x has to be less than 8 and negative 2x has to be less than or equal to negative 4. Fresh copy of the negative 2x. Fresh copy of the negative 4. Now when we divide both sides by negative 2, we're going to switch from less than or equal to greater than or equal to, and simplify to write x is greater than or equal to positive 2, and we can still say x has to be less than 8 and x has to be greater than or equal to 2. We can write the two separate intervals, but I don't know if I'd want to. I'm going to write this, then I'm going to erase it. So just fair warning, I'm about to erase what I'm about to write. This would be negative infinity to 8. This would be 2 to positive infinity. And the and translates as an upside down one of those. And means intersection. If I'm at the intersection of two streets that I'm kind of, I have to be careful, look both ways, I'm kind of on both streets. If I want to be on both of them, I have to be at the intersection of them. So if it's in this one and it's in that one, it's where they overlap, it's what they have in common, different ways of saying it has to be in both of them to make it true. This is not an okay way to leave the final answer. There's a simpler way to write this using interval notation. So rather than writing it like that, shrink that down, put it up there, maybe graph it just to get an idea of what's going on. X is less than 8. That's everything, oops, parenthesis. That's everything to the left of 8. X is greater than or equal to 2. That's everything greater than or equal to 2. And it's got to be what got shaded both times. What interval on the number line got shaded both times? What do these have in common? 2 to 8. So that's what we write. 2 on the left, 8 on the right. That's the solution set to this compound inequality. Okay, it's what the solution sets to the two inequalities have in common. So it's more than just putting a symbol in between, finding the two separate intervals and sticking a symbol in between them. It's figuring out, well, what's the best way to describe this? It's that set of numbers, the ones between 2 and 8. Those are the ones, including the 2, not including the 8. Those are the ones that make it happen. So maybe the one with the and is a little bit more complicated than the one with the or. That's because and is more difficult. It's more restrictive. They both have to be satisfied in order for it to happen. Three-part inequalities are special cases of compound inequalities involving the word and. That's really what's going on. If I said negative 11 is less than 3x plus 7 and 3x plus 7 is less than or equal to 19, a shorthand way of saying that is to say that. Basically, we get both at the same time, because we're saying on the one hand, negative 11 has to be less than 3x plus 7, and on the other hand, 3x plus 7 has to be less than or equal to 19, but they both have to be satisfied. And when they both have to be satisfied, writing as a three-part inequality is an option, and it saves us about 25% of the work, because instead of having to do something to both sides here and do something to both sides here, that thing that we do just gets done to each part. So we do it 3 times instead of 4 times, and I think that's 3 is 25% less than 4, or something like that. So it's a little bit less work on our part. So let's suppose for the moment that 19 is not there. It's about to be there in a moment, so don't erase it. Suppose it's not there, and you're solving for x. What are you going to do? First step. Probably subtract 7. We'll isolate the 3x term. So it's subtract 7. And we will. Don't worry. But for the moment, suppose the negative 11 is not there. What are you going to do to both sides? You're going to subtract 7. So with this three-part inequality, save a little bit of time, a little bit of effort, subtract 7 from each part. And this will give us an equivalent inequality. This will be negative 18 is less than 3x. Scratch those negative 7s. And 12, right? 19 minus 7 is 12. There. All right. So for the moment, if I were at the board, I would cover this up. I really can't cover anything up, and I don't know if I want to erase anything. For the moment, well, maybe I will. Suppose that less than or equal to 12 is not there. What are you going to do to both sides? You're going to divide both sides by positive 3, and we will in a moment put the less than or equal to 12 back. Suppose for the moment that the negative 18 less than is not there. What are you going to do to both sides? You're going to divide both sides by 3. So, keeping that in mind, we write a fresh copy of the negative 18, and a fresh copy of the 3x, and a fresh copy of the 12, and we divide all 3 parts by 3. When we divide both sides, or all 3 parts of a three-part inequality by a positive number, you suppose we're going to switch it or leave it alone? We're going to leave it alone, since it's positive. 3 is positive. So less than there, less than or equal to there. Negative 6 is less than x, and x is less than or equal to 4. Just like that. And that gives us almost the final answer. It's just a matter of translating that into interval notation with a -6 on the left and a 4 on the right. There, if you pick a number, any number between -6 and 4, including 4 but not including 6, it should satisfy both of those inequalities at the top. Let's pick one. So I'm pick a number between -6 and 4, a nice one.
1.
3, 2, 1. Guess go with 2. I think I heard more 2s than anything else. So 2 should be a solution to this. So if we substitute 2 for x, 3 times 2 is 6. 6 plus 7 is 13. Does that work? -11, less than 13. That's true. How about 13? Is that less than or equal to 19? That's also true. There are a lot of numbers between -6 and 4. Any one of them would have worked, but 2 worked in that case. B part. Goodness, what would we do to all 3 parts to make this just a little nicer? Start off with. I think 5. I think deal with the fraction. I think that's the way to go with this. So multiply by 5. Multiply by 5. And multiply by 5. All 3 parts get multiplied by 5. And we get 15 is less than or equal to 9 minus 2x. And that's less than 30.
Less than or equal to.
Yes. Sorry about that. Less than or equal to, absolutely. There's no reason to drop that or equal to bar. What next?
You got to subtract 9 from each side.
Yeah, with a view toward isolating that minus 2x in the middle, subtract 9 from each part. Now we get that minus 2x all by itself in the middle. So subtract 9 from the part on the left, subtract 9 from the middle, subtract 9 from the 30, and we get 6 is less than or equal to -2x, which must be less than or equal to 21. And one final thing to do to all 3 parts. We need x in the middle. So divide all 3 parts by -2. Fresh copy of the 6. Fresh copy of the -2x. Fresh copy of the 21. Divide all 3 of them by -2. Leave the inequality symbols alone or reverse them. Reverse them. If I divided both sides of 6 is less than or equal to -2x by -2, I would want to reverse that. If I divided both sides of -2x is less than or equal to 21 by -2, I would want to reverse that one as well. Again, we hang on to the or equal to bar. I should be more careful there. -3 is greater than or equal to x, and x is greater than or equal to -10.5. Or Alex might just want the -21/2. There's one additional step you might want to do before you translate this into interval notation, and that would be to rewrite it so the number on the left is actually on the left. I'm not dividing both sides by a negative number here. I'm just saying if x is greater than or equal to -21/2, that means the same thing as -21/2 is less than or equal to x. And if -3 is greater than or equal to x, that means the same thing as x is less than or equal to -3. Once you have the lesser number on the left and the greater number on the right, then you can write the lesser number on the left and the greater number on the right with your interval notation there.